Hi everyone, today we have Eren Firat from EPFL. He's going to tell us about the effective field theory of perfect fluids.
Hi, thank you very much for inviting me here. I'm very excited to share with you the recent progress we've made in the last few months with Gabriel Como, Fanny Session, Brian Hemming, and Ricardo Ratazzi on the study of this very simple and well-known classical theory, which is the perfect fluid, and its formulation in the modern EFT language. And so this is based on a paper that was out 1 month ago on the archive, in which this talk is mostly based. And so this subject has been of interest for several people, for the community in the last 20 years or so, I would say. And there's kind of two main reasons for that. First of all, the perfect fluid is inherently effective theory. So rewriting it in this modern language enables us to treat corrections in a more systematic way, for example. But it's also the second reason, which is probably the main one, is it also enables us to try to understand it at the quantum level. And this is quite fascinating because unlike other finite density systems like superfluids and phonon and solids, which admits a very nice quantization, which follows all the traditional paradigms that we expect, when we try to do the same for the perfect fluid, we obtain very exotic and peculiar properties like UV-IR mixing and infinite degeneracies, which are very uncommon from a high energy physicist perspective, but which appears also in other finite density condensed matter systems like fractals, but which are way more exotic. And I think the fact that we observe the same kind of things in such a well-behaved and simple classical theory is quite surprising. And therefore, like studying it might tell us something about the perfect fluid itself, but also more generally about this the quantization and the 50 treatment of all these finite density systems. And maybe in the end it will tell us something about QFT, our understanding of QFT. And so I know that Ricardo Ratazzi gave a talk on a very similar subject a year ago. But since then, we made quite a lot of conceptual progress, and so we'll take a very different route on the subject of the talks. I think the two should be quite complementary. And really, the main idea that I've been following the talk is to separate in kind of two parts. First of all, I will focus on the classical level, where I will show what are all the possible ideas to try to formulate such an EFT. Because indeed, there is not just one, there are several ways to do it, which are subtly inequivalent, but all have some key properties which are a direct consequence of Euler's equation. And so it will enable us to understand better what is the relationship between the properties of the partial differential equations and the properties of the EFT. And using that, we can build on it to a possible quantum level, because if we choose the most appropriate formulation, it will be easy to understand how these weird properties come based on simple EFT tools, symmetry breaking pattern, and in particular, Boston's theorem to enable to understand the very specific spectrum that we will see. And so, of course, don't hesitate to bombard me with questions from the floor. But to start, I could maybe go to like a simpler question, which is what is hydrodynamic, what is the perfect fluid, and why do we want to study in the EFT language? And so hydrodynamic is just the study of the long distance behavior, long time behavior of finite density and finite temperature medium system, where we expect a universal description in terms of a few macroscopic variables, which are well known to everyone, which is the pressure, the density, the velocity, and so on. And the fact that we observe this very universal behavior is a consequence of the fact that if we look at the system with the path and try to look at fluctuations around it and modes. There's kind of a strong separation between, on one hand, the modes which are not associated to any conserved quantities, and the modes which contain the charge, which are charged under the symmetries of the system. Because the ones that are not charged, they can dissipate in the path very fast, like time scales. So, for example, if it's a bath which is in thermal equilibrium at the time the order of the temperature time scale. While if the mode contains some charge, the only way to get rid of them is by transport, which can take a very long time if we look at long wavelength mode. And therefore, the dynamics that we obtain in this sufficiently long time is just continuity equations for this conserved quantity. In particular, if you go to the relativistic description, it's very easy because then it's just the Noether's conservation. And so if we focus, for example, on just a fluid with energy and momentum conservation, then the equations are just the conservation of the stress energy tensor, where we take the stress energy tensor to be just a function of this hydrodynamical variables. But here I wrote the velocity in terms of the four vector u mu, such that we will be able to write things in a polar way of Lorentz. And when u is normalized to be -1, and in the non-relativistic limit, it's just 1 and the velocity. And then so we have, for example, if we go to 3 + 1 dimensions, we have 4 equations and 5 variables. And so we need some additional equation, which we call the equation of state, to have a complete set of equations. And usually it's given as a relation between the density and the pressure. And this is where like the freedom lies in what kind of fluid you are describing. And so now we have a complete set of equations, which we can look at from a slightly different perspective, which will be useful when we go to the EFT language, which is by introducing some auxiliary field or variable P, such that P and rho will be a function of additional variable, and it will follow, and we introduce it by asking it to respect some relations, which you can probably see to be just the standard thermodynamical relations for the temperature and the entropy. So this is now we can, if we think of rho and P to be just a function of P, then we can think of the stress energy tensor to be a function of P and the velocity, which we can package in one vector, which I will call psi mu, which you can figure out as the temperature current. And then we can think of it as the stress energy tensor to just be the most generic function of this vector psi mu written in a derivative expansion. Of a leading order, when just obtains very good structure which are possible, and this is just the percentage tensor of the perfect fluid. And then if we go to higher order, we can get Navier-Stokes equations and so on and so on. And then if we stick at the first order, there is some conservation law. One of the Euler's equation is just the total current, and just using this property, we can identify it to be the entropy current, such that this current is conserved in an automatic way at leading order when we just have Euler's equation. And then we can repackage the three remaining Euler's equations in a convenient way for what I will say later by introducing this vorticity tensor, which is just the curl of this vector psi mu, such that now the rest of Euler's equation can be just written in this very small and nice form. And so what we observe is that we have a structure which really follows the principle of effective field. In the sense, we have a few IR fields which describe the theory at long distances.
Second equation in the last slide. Second equation.
Yes.
So moving rate is verticity.
Yes.
But usually it's multiplied by current. Not by momentum. Psi is momentum.
Like psi is like the temperature current. Yeah. it's T times the U. It's the same thing as what you're saying at the leading order because everything is proportional to the velocity. So this is the reason.
And you took it about barotropic flow.
Yes, exactly. Yeah, so yeah, you could replace here this by the velocity at leading order. It's the same thing. I just wanted to talk with what I was saying. Yes, so we already followed the principle of EFTs, but not the language of it. And so we can try to go to reformulate all of this in the language of EFT. And there's kind of two different directions that are followed, that have been studied in the last like 10, 20 years. One which I will call the more pragmatic approach, and one more conceptual approach. And the pragmatic approach is to go to finite temperature case and look at energy much smaller than the temperature and try to develop some EFT description, which in this regime we expect to reproduce hydrodynamics. And so this is an interesting line of research with a lot of work. And for example, if you're interested in, there's this review by Paolo Coelho on the subject, which explains it. And a lot of people here are very familiar with this work. And the thing is that because we have dissipation and finite temperature, it's not so easy to write in EFT, and we cannot use the standard Lagrangian formalism, and we need to go to the Schwinger-Keldysh formalism. So things that are more complicated to understand, and in particular, what are the IR variables? It's not so straightforward to understand, and it's actually something we've been working on. So if you're interested, we can talk about it after the talk. But then here we will go to a more conceptual approach, which is to go to the dissipationless limit and really go to study the perfect fluid then. And this is much simpler because now we can just talk about Lagrangians in a more standard way. This is also interesting because if we think of it as like a low temperature limit, it's a regime where we could expect quantum effects to become important. However, it's also less motivated phenomenologically and experimentally, because when we go to low temperature, we don't see perfect fluids. We see superfluids and solids and no perfect fluids. So one of the questions is there some fundamental reason why we don't see them? Or is it maybe just that it's technically difficult to realize in nature because of some of the properties? And so these are kind of the questions which comes with this more conceptual approach that we will follow now. But so if we try to do that, we have a first difficulty that emerges directly, which is the fact that we need to introduce some additional degrees of freedom. In the sense that we cannot just use this hydrodynamical variables that I was telling you about. And the reason is very analogous to what happens when you consider the rigid body. Because when you study the rigid body, the dynamics is just a function of the angular velocities in the different directions. And if you write a Hamiltonian, it's just going to be a function of these angular velocities and some inertia time. However, if you try to derive a Lagrangian for it, you're forced to introduce some additional variables. And for the rigid body, it's easy to understand them. It's just the angles themselves. Because if not, you cannot write basically canonical pairs and go to a Lagrangian formula. And here the same thing kind of happens, but for the perfect fluid. And so there's different ways to deal with that and introduce variables. And this is where kind of the original ambiguity comes from. The easiest, conceptually simplest idea is really to think of we are in a finite density system with some symmetries, and in particular, a boost is broken. So we can describe the dynamics in terms of the boson-boson associated to the boost and the additional symmetry. And for the case of the, and this is basically what is the path which is followed to study superfluid and solid and things like that. And so for the fluid, what is the situation? So it's quite easy to understand because we can take the physical space and we have the fluid living in space, and we can label each fluid point by a set of coordinates. But, and so then we have these coordinates, which form a map from the physical space to this internal space. And so they form a set of fields from which we can build the Lagrange. And the thing is, there's a huge symmetry group that comes with that, because if we move around the fluid points in this internal space, without doing any compression or dilatation, we get a configuration which has the same energy. And therefore, this is a huge symmetry group, which is a group of volume preserving diffeomorphism. And so when we write the Lagrangian, we need to write something which is invariant under the symmetry group, which forces us to write everything in terms of one single vector, which is a function of this coordinate of the spheres. And this vector is trivially conserved in the sense that it's not dynamically conserved, but topologically conserved in some sense. And so we can interpret it as the entropy term. And so here I'm going a bit fast because this is not the approach that I will focus on the most here. But the idea is that then you can write a Lagrangian as a function of this of the entropy current as written here. And we can derive all the properties of Euler's equation from that.
The 3 plus 1 b would be cubic.
Oh yeah, here it's in yeah, we would have one more. Here I wrote it in 2 plus 1b because I will focus on
What does the leading term in the Lagrangian look like in terms of capital S?
I mean just
But sigma has a bit.
oh yeah, here I wrote it in a way. Yeah, so sigma has a value, which is the fact that, for example, if you take the trace, you can just label each point by their code. So sigma of x has a value which is just x. And then the fluctuations around that can be interpreted as the goldstone associated to this big symmetry.
Just to clarify, is it about incompressed or compressed?
So here is no here both.
It's one of the incompressible fluids. Dynamical group.
Yeah, so here it's the fact it's the symmetries. If we do any transformation which do not do any compression, this is a symmetry. If you do some compression, then it's not the symmetry of the action. I think what you're saying, I will come to it. It's I think it's from I will talk about a different perspective where volume preserving will come in a different way, which will be related to the compressible. But here it's just the fact, in this perspective, it's just the fact that if we, it's the symmetry is that if we don't do any compression, we get the same energy. So here it's not incompressible. But so there's this different approach, which is more in the line of the way we wrote this dispersion tensor for the perfect fluid before, which is the fact that okay, we said the dispersion tensor is just basically the most generic function of the temperature and the velocity, and so we try to apply the same thing for Lagrangian to write it as a function of the vector xn, which is the temperature and the velocity. And so we have this very generic Lagrangian, but as I said before, we need to introduce some variables, some more macroscopical variables to describe the theory so that I was talking before. So to do that, we decompose this vector in the most generic way, which, okay, in 2 plus 1 dimension, it would just be like that with 3 fields, 3 real fields, 1 longitudinal and the rest, which you can kind of interpret it as the transverse part. So this is just the most generic way to decompose locally.
Terms, they're both derivatives. What's alpha?
3 fields. It's 3 scalar field. There's 3 components basically. So it's a way to parameterize. I'm basically decomposing the vector in terms of longitudinal and transverse, which here doesn't have a lot of physical meaning at this point, but it will become more physical. And
This
if
is
you
in 2 plus 1.
here it's in 2 plus 1, and if you're doing 3 plus 1, you should add like 1 additional field, of course. Like here in front of this field, you should have 1 additional field, And if you go to higher dimension, you should have more and more fields. But the thing is, there's some accident from the fact that in 3+1 dimension, there's an additional conservation law, which is the EFT conservation, which enables to reduce the number of fields needed to only 3 again. And therefore, we can parameterize this current in terms of the 3 fields like that, both in 2+1 and 3+1 dimension. Such that actually, from this in this formulation, the two cases are quite similar. And a lot of what I will say applies to both cases. Not everything, but a lot of what I will say applies to both cases, and so I will focus on the 2+1 dimensional case for simplicity. So I wrote this vector using these 3 fields, but it's nicer if we take alpha and beta and write them in one single complex scalar field for the interpretation later on. So this is what I do here. So we have one scalar field and one complex scalar field. So we still have 3 regular scalar fields. I just changed notation. And so here it's nicer because so this is just the longitudinal part, and this is the part associated to the vorticity. And in particular, the vorticity is given by this. And so now that we have this decomposition, we can compute the stress energy tensor associated to this Lagrangian I just showed you. And we get this, which again has the form of a perfect fluid. If we interpret this to be the pressure and this to be the temperature. And then this is just reproducing what the fluid. In particular, we can identify what the entropy current is, and it's given by this function, the 2p prime times time mu, which is just the derivative of the action, the functional derivative of the action with respect to the vector time, and which is a concept like equations of motions, which here I can just write them in this way, which is the same as before. And so this is quite nice because we see that if we try to add derivative correctness to this action, which is just by having a function which is the action to be a function of time mu n of derivatives, then all of what I said is not really changed. It's just that the entropy current is now a different function, and it's now just defined in this way. But then the definition of the tensor is the same, and the equations of motion look the same. So writing correction is very simple in this moment. Of course, here it's just corrections which do not take into account statistical fluctuation and dispersion. Because the Lagrangian of the mechanical system. So this is so this description reproduces hydrodynamics and Euler's equation and perfect fluid. But we can go a bit further and study what are the symmetries of this description. And the thing is, we constructed it. The Lagrangian is just the pressure, and it's a function of the vector psi mu. And so any transformation that leaves this vector psi mu is a symmetry of the action by definition. And the fact is, this decomposition I showed you before is the most generic one, but it's not a unique one in the sense that we can put part of the longitudinal modes in the field psi or a chi or phi. And so we can do a whole set of transformation between the two. And they are given here. In this transformation with the vector psi mu involved. And how, what are these transformations? So if we take, so here it's the symmetry because function.
Is psi mu the physical variable or pi and phi the physical variable?
We take chi and phi to be the physical variable. And you can try to think what happens is if you don't want to take them as the variable, that you want to take the vector psi mu as the variable. That means you try to gauge the symmetry, and what you obtain is a trivial gauge away everything.
As a classical theory, we had a theory of psi without pi and phi, right?
Yeah, it's the same thing as for the rigid body, where you need to introduce the angles in the Lagrangian. Of course, the Lagrangian is only a function of
The symmetry does not act on psi.
No, it only acts on the field.
So the value of psi at a point in time would be unchanged if I gave it the symmetry. So I would indicate that I remove all the. Right, wouldn't psi still be observable? You said that gauging the symmetry removed all the.
When I quantize the theory, my point is when I quantize the theory, it will, yeah. Okay, maybe I can show you what are the consequences of this symmetry to show you that we should not think of it as a gauge symmetry. So one of the consequences.
What are the scalars? What measurements should we do to compute that? You're saying that every fluid has some phi dagger that we can measure at long distances? What are those?
Well, these ones, they would be associated to the longitudinal phonons in the fluid. And these fields, they will give you some vorticity fluctuation. This is basically what will happen.
Maybe I can comment on this to put it in
Mhm.
the standard framework. This
Yeah.
side, one form of it. Therefore, by Darboux theorem, it's supposed to be expressed in three quantities. So they go
Exactly.
H, right?
Yes.
And psi is a canonical momentum which transform on the gauge transform by height. So what you really measure is kinematic momentum and homotopy of height, not height itself, but change of height.
Yeah. I guess. And so if we take, so these transformations are generated by a generic function of phi and phi dagger. So if you take f to be just a constant, you're just generating shift of this function chi, and it's just a U1 symmetry, and the conserved current is the conservation of entropy. But then you have a whole set of transformations which are dependent on phi and phi dagger, and in this form, this is just volume preserving diffeomorphisms transformations of this phi dagger manifold, which you should not be confused, are not the same as the volume preserving diffeomorphism I was talking about before, because there's different variables and the physical consequences are different. And so there are two different symmetries that come in the two different descriptions. And they come with a very large set of conserved charges. And the fact that you get such a big symmetry group is actually quite important and is related to the fact that Euler's equations have a very large set of non-trivial solutions. Indeed, when you just think of the solution where you have a fluid at rest, so you have this vector psi is just temperature 0, 0, 0, or 0, 0 in 2D. Then to build such a non-trivial finite density solution, you need to have a solution of this form. But chi depends on time, and it's basically the same thing as when you try to build the solution for the superfluid, where your scalar field we have there mu times t, where mu is the chemical potential. So here it's just the temperature in terms of instead of the chemical potential, but it's the same idea of if you want a finite density solution, you need to break some of the symmetries. So here the Hamiltonian, the time translation, but then combine it with some of the internal symmetry to form an effective time Hamiltonian that will generate the effective time translation, and that gives you a notion of stationary in the same way as what happens for the superfluid.
Where does the quantization come? Like I would have thought that like the transformation would just be as I would nature.
What did you say?
Like, why is it U1 symmetry?
Yeah, instead of being an R.
Yeah, what is the one symmetry? Oh, okay. I mean, it's a shift symmetry of chi. Yeah, okay.
Is chi a real variable or a periodic?
Chi is a real variable.
Normally, this symmetry quantization of number of particles, and then quantization on side quantization of particles.
Yeah, but here I'm just,
In circulation. It's also consequence. So it's a gauge thing.
okay, maybe we should talk about after that. But, okay, so we have, if we take this, combinations, then you have the effective Hamiltonian, which enables you to have a finite density solution. But now we have all the other finite density solutions with non-trivial vorticity. For example, you can build some hurricane solution with a velocity profile that depends on the radius r and just turns around like this. And this is also a stationary solution with the velocity being constant. But however, if you try to compute what will be the fields that gives you the solution, they also depend on time and so on. And so you need to combine the Hamiltonian with some of this very large set of charges, and so this the effective Hamiltonian, which will give you time translation in the stationary to give you a stationary state. And so this is kind of like the why we need to have a very large symmetry group when we describe the perfect grid, is because Euler's equation have a very large set of non-trivial stationary solutions.
So, yeah, I'm trying to understand that statement that it's diff of phi means that you have many solutions. So are you saying that I can act on the kind of trivial solution with a phi diffeomorphism to generate this vortex or
No.
okay.
It's because they will not change your velocity.
Right. Yeah.
What they mean is when you have this very non-trivial solution where things are moving around.
Yeah.
To have like this, to understand what is time translation, like the stationary, why, in what sense it is stationary, so it doesn't depend on time. You need to find some effective Hamiltonian, which is conserved. And the thing is, because the solutions depend on time, it's not just the standard Hamiltonian, it's some combination of the Hamiltonian and this volume preserving diffeomorphism, which will give you your effective Hamiltonian.
But it's this phi, which I can't observe phi, I can observe the velocity. So that was my question, whether you can observe phi there. Yeah,
The velocity field is activated, so it's somehow.
but it's the velocity field is the thing that's, like, the thing that's stationary and also the thing that I can observe. Yeah.
And in the superfluid case, you cannot observe chi, but you have the derivative of the scalar field, which you can observe. That so your effective Hamiltonian is H minus mu Q and it's basically the same like this for the superfluid, but for more general situation. Okay. And so the question that you can have is, are these two formulations equivalent? They the same thing. And the thing, of course, is at the level of hydrodynamic variable, with the velocity, the pressure, the density, both descriptions gives you the same, describe the same solutions of Euler's equation. And this is by construction, because this is what we require each time. And actually, you can find a Legendre transform that relates these two descriptions, where you do a Legendre transform between the temperature current and the entropy current. And so the two Lagrangian are related in this way. However, if we look more at the level of this more microscopical variable, there is no GID that you can form.
What do you mean by microscopic?
I mean, not hydrodynamic, right? The field phi, chi. This phi. Yeah, this phi. And what I mean is that there's no one-to-one correspondence between the concept quantities and the concept currents in the two descriptions. And there is no one-to-one correspondence of the solutions even up to the action of the solution.
The second description you're talking about is the Schwinger-Keldysh description?
No, the Klepsch description and the Commuting description in terms of like the fluid and flattening the fluid elements. that I briefly mentioned. Well, we take the action to be a function of the entropy. So it's kind of two descriptions, where one where the action is a function of the entropy current, and one where it's a function of the temperature current. And this one is probably the most intuitive one, because we understand very well what this field sigma r, we are just labeling the fluid elements. But the other one is slightly less intuitive in the sense that we decompose in terms of longitudinal and transverse modes. However, it will be the one which is the most convenient to go to the quantum level.
But mustn't one of them be wrong?
What?
Mustn't one of these two descriptions be wrong? Based on the fact that they're not.
I mean, the two descriptions give you the hydrodynamics and.
But if they're not describing the same underlying physics, that eventually, then there's only one criteria.
I will show you what are the differences, which are very subtle, and so yeah, maybe you can say that decide that one of the two is wrong. But in some sense, you could also say that there's two different theories which reproduce the perfect fluid. And then there's some additional things in the theory, like this conserved charges and stuff like that.
So in
which
practice,
I
isn't the
think
problem
is-
that your S diff is not acting in the sigma theory? It's just acting
Yeah.
trivially,
Yeah, it's trivial in the sigma theory. And
and but you insist on saying that that these phi fields are observable, so you have to keep it in the.
So at the left is the theory where S didn't engage.
Yeah.
It's extra.
Yeah, so you.
You're right, it's not.
I don't know if you can say that in the, I mean, the left, in the first formulation, you don't have this.
But
There's
it's
no
not
right.
to say it acts as one.
And but, okay, even if you want to look at the action of the configurations of the action of the fluid field, you can see that actually in the second formulation, this is not the only solution that will reproduce the fluid at rest, for example. But there's other solutions which are not related by this transformation. So there's a set of solutions which are a bit more complicated than this one, which reproduce the fluid at rest, while in this description there's only one solution up to the action of symmetry, which reproduces the fluid at rest solution. So they are different. However, when we go to very high vorticity situations, like the differences disappear and both theories travel. So this is a small difference, which is a bit subtle, and indeed it's not super clear which one should be the correct one.
How many different solutions are there that describe fluid at rest? Right. Is there infinite or finite?
Yeah, infinite.
Not such a small difference. The difference by infinite degeneracy.
Yeah. I mean, small in the sense that what I meant by small is that if there's like some regimes where you don't see the differences, for example, the one of TCP, and also if you just look. Yeah.
There's some sense in which if I turn on a finite amount of dissipation and take the limit that takes out one of them.
Second.
Like if I have a small amount of viscosity, which is, and then I take the limit and that goes to zero, does that pick out one of them?
It's a good question. I'm not sure.
So that's sort of like how you glorious and they have a dissipated form. So
Yeah, and that formulation is a good point. When we take the dissipation less limit,
yeah,
what you reproduce is exactly this.
it's a co-moving guy. It's not like that.
Exactly. You reproduce exactly.
But it doesn't have to have any connection. So in real life, when hydrodynamics emerges, it's always finite temperature phenomena. Here he wants to try to make sense of some quantum theory that would be described by Euler's equation. But it's not going to arise due to the usual reasons of hydrodynamics arising in everyday life.
No, but
So it doesn't have to be a smooth, connection. It probably shouldn't.
But I would imagine that the gradient expansion, if I set the coefficient, like the viscosity is like a gradient expansion coefficient. If I take the limit, should it be like some way continuous or no?
Yeah, I guess in the sense that you, in both cases, you get Euler equation. But I think both.
Yeah, but he's saying that like you only get the co-moving coordinates by taking the dispersion.
I mean, if you take homogeneous action and you go to this dissipation limit where the theory factorizes the two branches, and you look at the in-out action that you take out of it, is exactly equivalent. So this is a good point because you could wonder, can you do something with this one? At final temperature, something to reduce this one in the dissipation limit, and maybe this could work, and tells us something both about the zero temperature case and about the final temperature. Okay. So what we're interested is mostly the looking around the fluid stress, because this is where all the weird properties come. And so what we do is we take this solution and we expand around it to small fluctuations, and we can take the quadratic Lagrangian in these fluctuations, and we ever derive what are the dispersion relations for the phonons associated to the fluid, which we could also get from taking Euler's equations and doing fluctuations around the fluid stress, and at the linearized level, we would get this equation where there is some longitudinal mode, which has a linear dispersion relation, and which is the same as the one of the superfluid. So this is like the part which is standard. But then there is also the transverse modes generated by the field phi, which have a zero dispersion relation, which is very uncommon, and it's quite related to the presence of this big symmetry and of the fact that there's all this macroscopic solutions with different vorticity profile, which means that you should have like the modes in the transverse direction have to have a vanishing dispersion relation. But this means also that it's very not clear what happens at the quantum level, because you don't have like a standard quantum harmonic oscillator form of your action, and therefore you cannot build a Fock space in the normal way. And so this is where all these ideas of UV iamically comes from as a hint from the classical level, where we have like modes with small momenta and large momenta, which would have the same energy. I mean, here we're doing the fluctuations around we have taken L is just T of chi squared. So this. And we take the solution of the stress and we look at linearized fluctuations around. And so
If I take this,
setting the form.
but if I take this down, I get up.
Exactly.
Just sound codes.
Exactly.
Linear sound codes, not fluctuations, but just sound codes.
Yeah. I mean, fluctuations is because fluctuations around this here. But it's the sum. It's just that. This action gives you the sum. So the longitudinal part is kind of easy to understand. So what we will do is we take the incompressible limit focused on this transverse mode. I'm going to try to study that. So if we take the incompressible limit, we also need to take the non-relativistic limit, because this is the limit in which incompressibility makes sense, which is just the idea that things move slowly, so we don't generate sound, and therefore we can integrate out the longitudinal mode and focus on the transverse mode. And this is the action that we get. So here's the kinetic term like this, where after, so here we have taken the non-relativistic limit and integrated out the longitudinal mode. And so here is the kinetic term of before with no gradient parts, as I was saying, and then we get some quadratic term of this form where there is some non-locality here. But this is a non-locality that we would expect because we will have integrated out longitudinal mode, which are gapless. So we have non-locality that should appear in our theory. However, it's a non-locality which is never on shell because this inverse Laplacian is a short notation for this. And the time part here, the time derivative can never be in the incompressible limit be big enough to cancel the Laplacian. And so we have a non-locality, but never on shell. And so, yeah, this is the Lagrangian that we get. And then the symmetries are still the one of before, which is the volume preserving diffeomorphism given here. So in just in case we get confused by this non-locality, we can introduce some auxiliary fields such that the action becomes local again. And if you were to UV complete this field A0, you would get back the longitudinal mode. But this was just a small comment. Let's go back to the action I was talking before. And to understand it, we can go to the Hamiltonian formalism and see what we obtain. So here, this part here, this is just the vorticity. And so when we compute the Hamiltonian is just a function of the vorticity, like this. And so what we see is, so here we have used the fact that we have computed the Poisson brackets of this action, and we have derived the Hamiltonian. And what we see is this with this Hamiltonian, with the Poisson brackets of the fields phi and phi dagger, implies this algebra for the vorticity, which we see they form a closed algebra. And this is quite important because this is what is necessary, such that the equations of motions for omega are just a function of the vorticity and are just the incompressible Euler's equation, which now can be expressed in terms of omega and kind of a continuity equation for the vorticity. So this algebra we can derive it. It's not a consequence of this formalism that I've given you, but it's a consequence of Euler's equation that we need to have this algebra popping up, and that the Hamiltonian is only going to be a function of the vorticity. So now going to the quantum level is quite simple because we can just replace this Poisson bracket by commutation relation, and then the omegas now still form the same algebra with commutator instead of Poisson brackets. And in the Hamiltonian, I've added some function to UV regulate. And we have our quantum Hamiltonian here. So here I've kind of done something a little bit fishy because this Hamiltonian is a function of phi is a quartic function of the field. Phi and phi dagger. So there's phi dagger phi, phi dagger phi. So there's kind of an ordering ambiguity when you go to the quantum level. And here we are making the choice such that the Hamiltonian is still a function of omega. So in this Hamiltonian, fields are not normal order in terms of that we have phi dagger phi, phi dagger phi. But we could have chosen different ordering. And this ordering is the one that preserves the symmetry, first of all, and preserves the structure of the Hamiltonian as a function of only the vorticity, which is why we take. Yeah.
So if you ordered it a different way, we get a anomaly in the current.
If you order it in a different way, yeah, you break the symmetry. Symmetries are not.
So you would mu JD would be some anomaly. Is there a meaning to that anomaly?
It's a good question. I'm not sure. Yeah, we focus on this case because this is like there's a way to keep the symmetry, so we're doing this way. And And also, I mean, it's to keep the symmetry, but it's also to have everything to be still a function of the vorticity, and not having the spheres phi to appear directly in the Hamiltonian.
So this choice is doing a lot of work because now in terms of phi, there's going to be a quadratic energy. And so it'll be easier to quantize. So just understand what is the symmetry that that is guiding you in choosing this normal ordering, but this as opposed to regular normal ordering.
So in some sense, the reason that we choose this ordering is just to preserve structure in terms of it's just a function of omega.
The structure, the fact that the commutator of two omegas is still omega.
Well,
Or what-
this, I mean, it's that the Hamiltonian is just a function of
Yeah.
one, but the symmetry behind it is the volume preserving diffeomorphism that I was talking about before. Because under this transformation, omega, which is with this, is inbound.
Is invariant to this. Okay.
So
Any
this
other-
symmetry implies that the Hamiltonian, the Lagrangian is only a function of omega. Besides the key.
I think it's this graph I got.
Yeah. It's, I mean, we have the vorticity tensor before, and omega is like basically take the zero. Okay, so now, as Lucas said, it's doing a lot of work because that means that there is a quadratic term in here. If we commute like one of the phi and one of the phi dagger here, what we obtain is the normal ordered Hamiltonian plus a quadratic term like this, which will give you a non-trivial dispersion relation. This. And the thing is, because the way we obtain it is by computing the fields and by this ordering issue. This is not a completely generic dispersion relation in the sense that it depends on the UV cutoff in a quite dramatic way. And this is the origin of the yeah. So yeah, it's here it's everything is made big by we have introduced some function to UV regulate, but then what is this function depends on what UV theory you have basically. So and normally when you build an EFT, things do not depend on this UV cutoff, and the only dependence is in some Wilson coefficient. Here the dependence is stronger. So this is not what we usually expect from an EFT, and this is kind of why it's not so EFT, not so effective theory in the standard sense, but we can still build it. And the thing is,
Around procedure.
yeah, in this way it is because. Of course, if you take just this term alone or this term alone, the symmetry is not preserved, but the full Hamiltonian is this is preserved the symmetry.
So the symmetry is 5 plus derivative.
Exactly.
But then if I have a function that removes below some cutoff, I do this transformation issue, I generate modes that have moment the structure of this cutoff.
And we come back to this, but this is yeah, so what happens is, so maybe first I should say a bit more of how we can interpret these modes. So we have this mode with this quadratic dispersion relation. And
but just to understand, so your way of regulating is not to remove the large momentum. I think it's just to replace that function f with.
Right.
yeah, here I take f to be a function such that it's one of the momenta and it goes to zero.
This regularization preserved.
And this regularization preserved. So what is this state, which is generated by acting? So if I give it some, I act with, I take, yeah, the 5x, I can here I will rotate in momentum space. I took the fluid from some of it. So we can think of them as raising and lowering operator in your top space to create states. And so what is the one particle state? So you can compute its vorticity and it's 0. And you can also compute the vorticity dipole associated to it. And here you see it's not 0, but it's linear in the momentum, and it's also orthogonal to the momentum. So basically, the interpretations of the states are states which are made of one vortex and one anti-vortex in the fluid, which are separated by a distance that depends on their momentum. And this explains what they are gapless, because when the momentum goes to 0, the vortex and the anti-vortex overlap exactly, and you get back your vacuum. And so this is why they are gapless. And at low momenta, you can compute scattering amplitudes between these different states, which I will call vortons, this vortex anti-vortex pairs, and you get some dipolar interaction. The thing is that because of this, the way we derived it, when we go to high momenta and momenta of order of the cutoff, the interactions become strong, and so we cannot compute like in the standard perturbative way corrections to this scattering amplitude. And to really make sense of the theory, we are forced to introduce some lattice regularization of some of the properties of the theories that to make sense of it. And this is basically what we have to do usually for theories which have some UVIR mixing, like fractons or stuff like that, where we need some lattice regularization. But first of all, I wanted to say that we can understand also the states from a symmetry breaking perspective, because indeed, when we look at this infinite set of charges associated to the symmetry, which is given here, we can decompose it in a basis of polynomials of phi's and phi daggers. And when we think of this Fock space that we have just built, what we see is that all the charges which do not contain any phi do not vanish when acting on the ground state of our Fock space. So this means that at the quantum mechanical level, this very big symmetry is spontaneously broken, even though it was not at the classical level. And so that means that we can build basically the goldstones associated to the breaking of the symmetry, and they are given by states of this form, where if we take n equals 1 is the state I was talking about just before. But there is also with n equals 2, so with two dipoles that are overlapping exactly, 3, 4, 5, and so on. And all the states with different Borton number, I could call it, have the same energy because they are related by some transformation. So the fact that we get these gapless states can be understood as the goldstone of this spontaneously broken symmetry. But because the symmetry is volume preserving diffeomorphism, this implies an infinite degeneracy in the spectrum. And these states are a bit weird because if you take, for example, n equals 2, and I decompose things into a relative coordinates and center of mass coordinates to a bottom. And what I get is a wave function for the relative coordinates of the two bottoms, which is exactly localized. So it's a delta function. So this normally would expect it to be outside the scope of the EFT, even though it's like it's a consequence of the symmetry. And to really make sense of them, you need to regularize it with some lattice. There are different ideas on how to do that. So let's go on the torus for simplicity. And so then the momentum is just integer numbers, and it's given here. So we had the UV regulator F before, but we also need to introduce some lattice to for IR. Yeah. I mean, the thing is, we want to regulate this kind of.
But I'm unclear why you're also putting it on a torus.
It's because we have all this weird UVIR mixing properties. And if we want to make sense of them, it's the only, I mean, what I've shown
You have a
you,
lattice in a non-compact space to regulate the divergence you're worried about or not?
in a non-compact space.
Yeah, infinite space, but the lattice. That also solve your problem, or some reason else you explore?
Okay, no, the reason why I put it on the torus is just for simplicity because if you have an infinite space, then everything is infinite because you have a finite density system. So to have like energy density and stuff to be finite and to the full energy to be finite and stuff like that. I put it on the torus. But yeah, the fact that I'm on a compact space, I don't think it's too important. Yeah, it was more for simplicity here in the procedure, and I put a lattice on stores. And if you do it in the standard way, with just discretizing the space, what you do is you break the symmetry to a much smaller group, which could be however interesting, because if you look at the Lagrangian at the leading order respecting this smaller symmetry, accidentally it gives you the same symmetry, so it gives you back the volume preserving diffeomorphism. So you expect that maybe on some time scales that are not too long, what you would describe still looks like hydrodynamics. However, we do not really explore too much this possibility, which breaks the symmetry. And the thing is, there is some more complicated regularization procedure, which involves using the SCN groups. And basically, the idea is that you have like a lattice which has a sublattice. If your lattice is n by n, you will observe the hydrodynamic on the scale square root of n by square root of n. And then you have some non-locality on like the sublattice. And this is a way that enables you to basically preserve the symmetry, which here it's a bit complicated, but because I'm already running out of time, I think it's not the center of the presentation I wanted to give. I'm not giving too much details on how you can regulate it, but what I mean to say is that there is ways to regulate the theory that preserve the symmetry. And so what I want, so to summarize what I was saying, so we saw that there are several ways to write an EFT description that describe the perfect field, which are slightly inequivalent. In these descriptions, we can write corrections in a simple way, but all these different EFT descriptions, they have some very large symmetry group, and this is associated with the fact that Euler's equation has a very large set of non-trivial stationary solutions. But however, at the classical level, the consequence of that is that the transverse modes have a vanishing dispersion relation. The transverse sound modes have a vanishing dispersion relation. And at the quantum level, that you get some UVIR mixing. However, at the quantum level, we see that we still generate some gapless spectrum, which is made out of this vortex anti-vortex pairs as fundamental excitations. However, the theory that we obtain is a theory which has UVIR mixing and an infinite degeneracy of the states. And so it's kind of is weirdly behaved and can only make sense when we think of it as some lattice model or some matrix model in some sense. And so what we obtain is a theory which is would probably be difficult to realize in nature because of these properties, but which mimic some of the properties of fractalic systems and so on, and which maybe all the fact that we are able to write all the different formulations to describe the perfect fit can also tell us something about this finite temperature of the finite temperature case, which is much more well behaved, and of the fact that there's different descriptions and how they look at finite temperature would be an interesting direction to explore in the future. Thank you very much for the time.
you have what kind of function?
Exactly.
Okay.
So here you should act with the charges, with this charges on the ground state, you get another one. Yeah, and then it's.
Do you have like what kind of- You said there was an infinite degeneracy.
Or like, I guess, how does the degeneracy depend on size? Like, is it similar to other problems?
And so if you have a lattice, it goes with n.
The same as graph.
The question is how. Linear size, like volume.
Yeah, and
Linear and systems.
No, but in the system, there is
What size of your resistance curve then goes then? Like,
here,
n by n or square root of n by square?
Yeah.
so the lattice is n by n, with the behavior is localized on like the squared by n by squared by n. So if you, I mean, it's on this sublattice that you observe hydrodynamic curve.
The volume of the system is, the spatial volume is what?
But yeah, so it's n.
The spatial volume goes like n. And the degeneracy also goes like that.
I feel like if you really want to think this is some theory that's motivated by hydro, but somehow it's like some one version, but it's like it's distinct from because in classical hydro, like these fives, I feel like they're not observable. I think these are
Okay.
stage, right? But the observable thing is like
The thing is, okay, there's some of the things that I told you, kind of this left formulation, which is the fact that the exact counting of the degeneracy is linked to the left formulation. However, the spectrum itself is not a consequence of this formulation, because if you take this Hamiltonian like this, which is the Hamiltonian of the incompressible fluid, and this commutational relation, which are the one that you want, such that the equations of motion for omega reproduces the continuity equations for the vorticity. Then from this, you can basically build the spectrum, because basically the omegas, they respect this algebra here, and so you can build the Hilbert space in terms of representations of this algebra here, and then you can look at different representation and what is the spectrum. And if you take the fundamental of this, it's gapped. But if you take adjoints or product of adjoints, it's not gapped, and it's gapless, and it's actually this node here. So it's not it's something which is not just this description. And if you use the co-moving description that I was talking about before, you can also derive this gapless dispersion relation. It's just it's much more complicated to understand how we can not as simple.
in the co-moving description, you also get the degeneracy.
Yes, but it's not exactly the same. It's infinite, but if you were trying to regularize, it's the counting doesn't go the same. But
If you didn't if you normal orbit your Hamiltonian from the start, then you wouldn't have PBI or
in some sense, you would have it even more, because if you keep the omega equals 0, so I would say it's even more.
would there still be a degeneracy?
I mean, in some, if you do that, in some, you're like get with
It's strongly coupled, right? The Hamiltonian is 5 to the 4.
Asked about this dispersion relation, you said this was an indication of UV iron mix. I need to make sure I understand that. I mean, if I took f is this function that appears in the Lagrangian, the function of derivative square over lambda square. So wouldn't the natural EFT thing Wilson coefficient in the EFT?
Yes, but okay, the level of the EFT can do that, but then the problem is that your theory is steady and strongly coupled at the top. So if you try to contribute loops or things like that, you have it could be very so if you, in the way you are thinking, it doesn't really work. And this is why you want to do that. Because basically there's the interaction terms go like it's on the interaction terms here is only weakly coupled because of the momentum. It's only suppressed by the momentum over the cutoff. So at the cutoff scale, it becomes a strongly coupled.
Interaction between pi and strong, but it's still a complete and counter term.
You're right. You're right. Let me be more precise.
This is the correct degrees of freedom, and you write here instead of writing the direction of the degree of freedom that directly has a generation that parameterizes that dispersion relation.
Do you think there should be a formulation where you think this directly?
Yeah, like both from you or something there.
What's the operator that makes these one particle state?
It's pi.
No, but I thought you said phi makes a two particle state. Makes a four particle.
Yes, I mean the one particle state would be gap. The vortex is gap. When you see it.
But the p-squared dispersion is these vortex and vortex.
Exactly. The things which are gases are like vortex. So it's a vortex alone, and it is a gap.
What's the characteristic separation of these vortex and vortex?
You mean between the vortex and the anti-vortex? Like the dipole is given by the momentum. And so, okay, the thing is, so the separation is when the vortex and the anti-vortex gets like really separated, this is when you reach the cutoff. So it's pair of separation, which is smaller than this.
Pairs can be approximated by a point line. Is a point line here? What's that about?
Yeah, this is what we're talking.
Why can't we write down the local effect here of these line almost?
I mean, local, I think we never do it because of the presence of this.
These are not the whole. These are not the whole. These are not the whole quadratic dispersion. What else?
Yeah, but the fact that it's non-local. So, if you said non-local, now it's non-local.
Yeah, I mean, you have this quartic Lagrangian for
Yeah.
phi, complicated one over p squared, but also you're trying to describe omega equals p squared. It's created by phi. It's very you have a lot of moving parts for such a simple dispersion relation. States created by phi.
I mean, it's a simple dispersion relation, but it depends on the cutoff also on this way. It's not so.
But it should be the parameter they have to give you
Just omega lambda squared f tilde of 0 is just some coefficient in the X.
Right, because rho m, f tilde, those are also dependent. They're also coefficients.
Yeah, okay. It's very,
you don't have this, such a.
But we don't have a formulation that this would appear, I don't think, I'm not sure, I would be very surprised.
You are overturning the whole model thinking. Theory.
Yeah, so can't you just say, okay, phi is the field I like. There's the symmetry that's non-linearly realized on it. So,
Yeah.
you know, there's going to be a quadratic term whose coefficient is correlated with a quartic term. But then that quadratic term will just put an arbitrary name, like arbitrary coefficient,
Yeah,
and it's
right.
this.
I understand what you're saying, let me try to. So just at the level of this dispersion relation, yeah, of course you can do that.
And the direction parameter.
But the interaction is a dipolar interaction, which is by nature non-normal.
But something to, not into the A0.
Exactly.
The field that into
And this is the longitudinal.
instead local population in terms of A0 and some local population.
Yeah, then in this way it's introduce a zero, becomes local. The non-locality is
It's not the effective field that is a particular quadratic dispersion because one is not the final.
Yeah, we have to go one step. But, yeah, so what you look like is
We just want a standard derivative expansion in phi, where you just manifest and see that dispersion relation in the first term, and then you fix the interactions by commanding the symmetry order by order.
that would be very nice.
Original graph you get after doing time. That's after doing after relativity. Because that's also like yeah, that looks kind of like a negative dispersion.
Yeah,
There'd be some way to read it off there.
If A0 has a vector saying,
A0.
Yeah.
A0 has no.
Because the energy goes down like they're being attracted to the pair attract each other. So if I take a Fourier transform, go to real space now, other force.
It's like the dipolar interaction. So it's the same force as like when you have positroniums interacting.
It's literally the same, like the fall off behavior.
It's the same long distance force between positroniums. The only difference with positronium is the fact that it's very short distances. Yeah, some contact interaction.
Yeah.
These things would be where are they there in the past? They must be there in the past.
This one?
they don't. Classical theory just had omega equals 0.
Yeah, that's what here has omega equals 0. It's because there's a spontaneous breaking, which happens on the different. That's the level of the spontaneous breaking of the symmetry due to solution.
But I guess contact, so I can also have.
I mean, there's no ordering of the five diagrams, you cannot generate. Yeah, and the way this quadratic term was occurring here was by commuting with fields. The way it generates. At the best level, omega equals 0. There's no, this is the part.
If there are no more questions, let's thank Eren again.